Good morning, ladies and gentlemen. Yeah, I'm Pierre Souchay. I'm working for the discovery team at Criteo. I'm also now working for authentication and authorization and security within Criteo. Today I'm going to talk to you about service mesh and discovery. You might think, why? But simply because whenever you want to deploy some load balancer on or service mesh, you need a working discovery in order to make it work at scale. I'm also the author of Consul Template RB, which is a nice tool to generate configuration based on Consul topology, which is very convenient, for instance, to configure tools such as HAProxy. We're first going to see a bit of history of Consul at Criteo, and we'll see then how we went to using service mesh at Criteo historically. And finally, we'll see how we built service mesh with HAProxy and Consul, and listing all the features we implemented already. So let's start with a bit of history of Consul at Criteo. So Criteo is basically a very large advertiser with many, many servers, many data centers, many kind of services, more than 4,000 different kind of services. So many, many instances of those services. We are dealing with a huge amount of HTTP requests every day on every data center. And we are also having a quite large Hadoop cluster to crunch all this data coming from the outside and to be able to display ads for people. So a very large infrastructure growing every day. But I'd like to go a bit about the architecture we are using for quite a long time at Criteo. So let's go back a few years ago, in 2013, where this is the kind of architecture we are using for all of our front-facing web application. So we are talking here about lots of those applications, dozens, and with many, many instances for each of them. One of the key things to think about is we are using what we called RTB. It stands for real-time bidding. So it's basically an auction system for ads. And whenever you go to a newspaper or something like that, we are performing an auction. We are part of an auction. And we have to answer very, very quickly to this auction in order for the business to work. So latency was always very, very critical to the business of Criteo. So basically, a request is coming from the north, from the internet, through various load balancers. At that time, it was F5 load balancers. So it's going to a web application. So yeah, here is more detailed stuff. So basically, the top layer of this diagram shows how we configure the load balancer. The load balancer was configured by various Perl shell scripts, huge ones. Also by data coming from Chef, which is our configuration management system we use at Criteo to deploy all those machines. And for those balancers, we did configure some health check in order to know whether the web application was behaving normally or not. So this was the part coming from the north. Then we had a very specific stuff built in our systems. We basically implemented a service mesh early in 2010 or something like that, where we had a database where we did register all of our microservices, so we could directly call them from our application. That's very important at that time because for one single request coming from the internet, you could generate lots of requests from your web application. So you had to talk to caches, to database, and to microservices. Just adding load balancer at that point in our system would add both latency, because of course you've got one hop more to go to the microservice, and also would, at that time, would cost a lot, meaning hundreds of load balancers, just to send data to a microservice. And since we had an architecture relying heavily on microservices, this would cost quite a lot. So we did some nice libraries in both C#, and JVM languages in order to talk to the systems. And finally, we had some logs, which are very important for our business, that were configured by chef and so on. So that was the 3 ways of sending data to other applications just for a single application. And this pattern was used everywhere at Criteo. So in 2015, we started adding containers. Why containers? Not only because it's cool and developers want it, but also from a business point of view, it's very useful to be able to avoid having typed machine, meaning that on a given hardware, you can run any kind of application. So we added containers running Mesos at that time, in a similar way as Tobias explained what they did at Yammer. So basically, we added containers, and a single machine could run several web applications, several microservices, and so on and so on. The question here is, in order to react quickly to the changes of containers, because when you provision a new machine, you spend a few hours waiting for the machine to come up, to be configured properly, and so on. So it means that it changed from waiting a few minutes to get a machine being up to a few seconds. It's very different, because all of our libraries, our client-side load balancing libraries we implemented, were relying on a database, and we had a polling time, for instance, of 10 minutes. So of course, it doesn't work with containers. So what we did first was doing exactly the same thing as Yammer, meaning we added a HAProxy load balancer that were getting information from Mesos and Marathon and generating a configuration. So everything is fine. We are adding an extra hop, but things are a bit more complicated than that. Because from our application point of view, yes, we can say HAProxy is now the intermediary step to reach our applications, but it gives you many, many problems. Because behind your HAProxy, you might have 10, 100 of instances. And for the other instances of your exact same service, but on bare metal, you don't want to dispatch this traffic blindly. So we had to implement, we had a real issue about how do we spread our loads across all services. And the thing is, whenever you have thousands of machines, you cannot just dump the legacy and say it's over. Because just moving from bare metal machines to containers takes a huge amount of time amongst your developers. We were also running Windows systems, and of course, moving to containers running on Linux is not something you can do in a 1-minute step. So that's where our existing systems that were behaving quite nice, but they were showing their limits. So provisioning time of all of our system was globally an issue. We had different ways of provisioning our F5 load balancer on the top as the service library. We had newcomers such as Mesos and containers that were showing limits of the database polling mechanism to perform client-side load balancing. And of course, we had issues whenever we wanted to move partially a system to containers while keeping the other on bare metal. So at that time, it was Another big issue we had, basically, was all those health checks were different in all of our systems, and sometimes they were not coherent. So we really need something else to move forward. So introducing Consul. So basically, Consul is a distributed key value store, such as etcd or Zookeeper. But it has also some very strong opinions about what is a service. So it already defines a structure, which is a service. And this service does not need to run on a specific SDN, software-defined network, meaning that you can mix containers, bare metal machines, cloud, and everything should work. So it's basically a middleware to expose and declare your systems. It also enforces something very interesting, which is the ability to define health check in a centralized way. When you are deploying Consul, you are basically deploying a Consul cluster, which is a group of servers in the same way as you could do it for Zookeeper, for instance, but you are also deploying some agents. And those agents are running on every machine at Criteo. And those agents are also responsible for checking whether the services they are hosting are working properly and dispatching this information across Zero Cluster. That's very interesting because whenever you are reaching some scalability limits, each of your health check has to be done by each systems. And here you have a global view of what is the healthiness of a given system. So it's very important for us. It also provides some very interesting features, such as being notified on any service of the platform whenever something changes. Meaning that the database polling issue we had, saying, oh, do I need to poll every 10 minutes or every 1 minute or whatever, disappear. You can be notified whenever the service you are targeting is changing. So that's very interesting as well. And of course, in the same way as etcd or Zookeeper, it has fault tolerance built in, meaning that it's a good candidate for using it on very large infrastructures. So the step we took was basically registering all of our systems within Consul. So we had data from Hadoop, we had system deployed by Hadoop, by Chef, by a tool we made by ourselves, Criteo deployer, by Mesos. So basically, we registered all those services. So now we are talking about something like 270,000 different instances of services, which is grossly 4,000 different kind of services. At the same time, we added health check. So basically, every service was responsible for saying, oh, I'm OK, or I'm not OK. And we added lots of various information that was really useful for what has been described by my colleagues Pierre and William yesterday, for instance, to provision load balancer automatically. Oops, sorry. Yeah. The step 2 was to port off all our client-side libraries to perform this load balancing. So we had libraries to perform HTTP load balancing, client-side load balancing. We had Kafka libraries, database access, memcache, and so on and so on. So it took quite a lot of time as well. But so instead of relying on instead of using the data published in some database with freshness not very up to date all the time, instead we use Consul to get the notification in real time about what is the service I'm targeting and how does it change, including in its healthiness. And finally, William and Pierre on their team did implement load balancer relying on Consul, meaning that now we have, instead of having separate systems, Consul is now a big middleware to guess the state of all the services within Criteo. That's very useful because it means that you can easily replace, either by client-side load balancing or by a classical load balancer, your system and get the same view. It was not the case before, and it led to many, many incidents in the past. So when we did this, it took us roughly 1.5 years or something like that. It was really painful. We had to put lots of optimization into Consul to make it work reliably. But basically, we had a full view of everything that was going on in our systems. And everything was running on top of Consul, meaning Consul was distributing this information about healthiness of all of our services across the whole organization. So it was really good, and we really enjoyed this moment. But the thing is, still, we have a bit of issues, especially regarding our client-side load balancing libraries. So it's basically small pieces of code running in our applications, but it's very, very sensitive applications. If you heard about Keep Alive and stuff like that, you know that just load balancing HTTP data is not a trivial task, especially when you want to do it with millions of requests per second. It means that all the code we have written for C# or JVM was very sensitive to changes. Whenever you were changing a single comma in your whole code base, it was very risky, actually. And it is very risky. So we have to be very, very careful about the changes we are applying. And furthermore, we did implement it for performance, meaning that, for instance, adding TLS or this kind of stuff is almost impossible. So, and finally, we are using, for now, 2 main languages at Criteo, but people say, I like to use Golang, I like to use Rust, I'd like to use Python, Ruby, and so on and so on. And of course, this doesn't scale up, meaning that we don't want to port those libraries to every language. So having another way to do this with performance in mind would be quite helpful. So 1.5 years ago, the HashiCorp, so the builders of Consul, did introduce Consul Connect. So basically, what is Consul Connect? It's the famous fashionable service mesh infrastructure system. So it's basically creating sidecar applications that will handle the whole connectivity of your service, that will introduce TLS, that will introduce service discovery embedded, and so on. And basically, how it works is you've got my app 1, and instead of adding this complex piece of code, client-side load balancing, you are just talking to localhost, and this localhost will forward your request to the various services you are targeting. So that's the kind of view you have, and of course, Consul is driving all of this because he has a clear view of the whole topology of the whole infrastructure. And furthermore, it adds some benefits for us, which is, for instance, adding TLS for free with a rotation and so on and so on. And it also had some authorization mechanism. That's quite interesting because in current architecture, heavily relying on microservices, it's sometimes very, very hard to know what is the impact of a system being faulty. I mean that a microservice can be called by another microservice that can be called by a real app. And knowing that whenever your microservices is not working anymore, what are the possible impact of this? It's a very, very challenging stuff in modern architectures, being able to decide what will come up after one service is down. And having a way to authorize systems would allow you to create graph of calls, for instance. Of course, lots of people are already using it. They are using Zipkins or tools from the Finagle family or whatever, but basically, it's very, very hard to have this and to be sure that you didn't forget anything in your infrastructure. So, I'm now introducing HAProxy Connect. So HAProxy Connect is what? It's an implementation, an open source implementation of Consul Connect with HAProxy. So basically, the reference implementation of Consul Connect is using Envoy. But we had a few issues with Envoy, deploying it in our old systems, for instance, but also having the ability to talk directly to people from HAProxy technologies is a big advantage for us. And furthermore, our network engineers are very familiar with HAProxy, less so with Envoy. So we decided to implement it by ourselves and then to transfer it to HAProxy technologies. Yes, sorry. Whoops, wrong. So this tool is going to be responsible for creating the HAProxy configuration, listen all the changes into the Consul topology, adding TLS for free between all your nodes, and is going to be compatible, of course, with both bare metal as well as any container system, meaning Kubernetes, Mesos, or whatever you want, and cloud, of course. The idea behind it as well is to keep it simple. Consul Connect is a service mesh system, but designed to be understandable by normal users. Meaning that it doesn't come with a full bloat of features, it just does a few things right. So here is how it will really work. So basically, we are getting the same schema as the first one, which is application 1 wants to talk to service 1. So basically, we are creating a HAProxy Connect sidecar system. And this HAProxy Connect system is going to create a configuration file for HAProxy and send the commands to HAProxy to be updated whenever those targets, here service 1, will be updated. And encapsulating all of this within TLS. On the service 1 side, HAProxy will be responsible for getting in its front end the incoming TLS traffic and sending to plain text to service 1 itself. So it gives you the ability to get mutual TLS because Consul will be responsible for sending client and server certificate on the TLS side, meaning that both server and client can authenticate themselves and be sure who is calling it. So the client validates the server it is talking to, and the server knows the caller well. So Consul also includes the ability to rotate those certificates and does it periodically, meaning that those secrets are not fixed in time, which is very important as well. And for those using HashiCorp Vault, it also supports delegating this secrets handling to HashiCorp Vault as well. So basically, how does it what kind of configuration are we doing here into HAProxy to make it work? So this is exactly what happens in the system. So basically, we are on the service 1 side, so the target. We are creating a front directive into HAProxy. This front directive will send the data to backends, and these backends will have only a single target, which is localhost on a given port. So basically, the port, the actual implementation of service 1. And all of this in plain text. So for those who really want to know, that's the kind of configuration it's going to generate. On the application side, so the client, there's a front end in order to receive data from application 1. And in the backend side, there will be all the instances of the service one we want to target, meaning that this part is very dynamic. It's going to change every second. In our systems, for instance, we've got services where we've got more than 2,000 different instances, meaning that those things do change all the time. And HAProxy Connect will be responsible for updating this information in live, reaching the correct targets every time. So this is the kind of configuration it will generate into HAProxy itself. But it's not over, because of course, your service one can also be a client of other services. Your microservice can use other microservices, database, and so on. So it means that, of course, by injecting your topology within Consul, you can say, but I want, yes, I am a server, so I'm going to answer to requests, but I also want to target those services. So in that case, everything is kept within the same HAProxy instance, and we will generate additional front-end for what we call upstream in the Consul language, meaning HTTP localhost targets to send requests to service 2 or service 3 and so on and so on. And all of this will run within the same HAProxy program. So now, what about authorization? So authorization is done in Consul Connect with the term intentions. Intentions is basically a way to say service one might be called by my app, but I don't want my other app to call service one. So it's a very important piece within Consul Connect. And it really allows you, on the long term, to create graph of your whole infrastructure. And that's where it becomes interesting. And as I told you, there's a mutual authentication with TLS, meaning that you are sure that my other app, because it shows to the target its certificate. So service one can be sure that the application which is calling him is the real one, because a certificate has been given. So in order to do that, what we did was implementing SPOE mechanism. So an HAProxy Connect is going to listen for SPOE requests, validate it, and allow the request to pass to the service itself. So what is SPOE? SPOE is a way of offloading some work to another agent called SPOA, and to perform some kind of validation and stuff like that. So in HAProxy, it can be used for authenticating, I think, for scanning requests from the internet, and so on and so on. So what we are basically doing is we are configuring HAProxy to use SPOE, using HAProxy Connect itself as an SPOA, meaning agent. So it's basically receiving requests from HAProxy to validate whether the incoming request is authorized or not. In order to do that, what it does is it decodes the certificate from the client, extracts the name of the caller, perform a call to Consul to validate that the intention has been properly set for this service. And if it's not OK, it's basically closing the connection. So a bit of under the hood of how this whole stuff is working. So HAProxy Connect basically generates an initial HAProxy configuration. So a basic configuration with the SPOE configuration, the control socket, and so on and so on. Then it starts HAProxy. And then it starts the data plane API. Yesterday, Marco talked to you about the data plane API. So we are using it in order to control HAProxy. So Data plane API is just basically, just for to remember, REST API to control HAProxy without the need for creating a configuration file, handling reload, and so on and so on. So it removes all the complexity of talking with Socat and friends to send commands to HAProxy. So here's a few of the optimizations we put in these systems. So first, of course, we are over-allocating the slot of servers, meaning that Consul is sending us lots of updates, sometimes several per second. So we don't want in HAProxy, whenever you are changing the number of slots for backends, you need to reload HAProxy. And of course, we want to avoid that as much as possible. So we over-allocate the slots of backends per power of 2. So we can just enable and disable the service without reloading HAProxy. We also apply a third mechanism, which is in order to be sure that HAProxy really understands what we mean, we simply send all of our commands to data plane API, compare to the results we expect, and if it's not working, we reload it. It gives us the ability to be sure that HAProxy has the exact state we want to be applied. And whenever something is changing in HAProxy, we are sure that even something is changing on the wire, everything is going to work as expected. What we did as well is this system, of course, expose the stats from, you can expose the HAProxy stats page, as usual. But we also made an exporter compatible with Prometheus that expose all the metrics from HAProxy Connect, including all the requests for egress and ingress. So it's a small capture of one of our systems for egress. So application 1, so this has the statistic for application 1 sending requests to service 1. So it shows, of course, the number of requests per second, the in and out traffic, and the response code with statistics for everybody. And on the other side, on service 1, you've got per ingress service the details of the statistics, the response code, and so on, the incoming request per second, and so on and so on. Anyway, you can create very easily those dashboards with all the Prometheus statistics, or if you prefer, you might use as well the HAProxy stats page. But here you already have some kind of meaningful metrics. On the log side, we also capture the output of HAProxy and redirect it, so you can redirect it to syslog or systemd or whatever your favorite log system. We are doing this and sending it then to Kibana in our case. So we are testing this new piece of software for something like 2 months in our pre-production, and we are using it already in production at Criteo for something like 1 month. So it's working quite well. On the performance, I had no time, unfortunately, to do some benchmark, but basically it performs better than Envoy with Consul Connect, which is already quite nice. We have around a 20% improvement both in CPU time and throughput. However, it has some kind of extra latency compared to plain HTTP as we did it in our client-side library stuff. So everything is open source. In order to deploy it, in order to create it, we also had to create SPOE library for Go, because everything is written in Go. And of course, all of this is open source, and we are now talking with HAProxy for them to maintain HAProxy technologies, to maintain those projects on the long term. And thank you to Aztec, which is the main developer of the system. And of course, we will be glad for any people wishing to use those kind of service mesh technologies to contribute to the project. Thank you very much.